Okay, good afternoon, everyone. We missed out few classes earlier. I will try to compensate for that. I'm planning some extra lectures also for completing the syllabus. Okay, so last few classes we discussed about brushless DC motor and DC motor with brushes. We'll see the speed control aspects of DC motors because remember these DC motors will be used as actuating devices in mechatronic systems. Now, whenever we are using these DC motors as actuating devices, these will be either directly connected to the load or these will be connected to the load via the intermittent transmission elements like maybe a gears with lever, or these will be coupled with some of the hydraulic or pneumatic systems in between, or you will be having some mechanisms in between. So ultimately, we need to control the speed of the DC motor so that my actuation will be as per my requirement. There are various methods of speed control of DC motors. Here specifically we'll be focusing mainly on microprocessor based DC motor speed control systems. This is our DC motor, as you can see, and this is called as the block diagram representation. We will be studying these details of control systems in our 5th and 6th units. We'll just have an overview of those control system representation. So these are called as, this is called as, all the three block diagrams are called as the block diagram representation of the system, in which the system elements or system components are represented in the form of blocks, and those are connected with the help of arrows. Arrows indicate to you the signal propagation direction, signal direction. And as you can see, you have from the left side, if you start, this is the input or the desired input, and this on the right hand side, the arrow that you can see is the actual output. So this is the desired output and this is the actual output, and in between I have a control system. Now this motor is called as my system, so to say. Motor is called as my system, and D2A converter, amplifier, these are called as my control elements. Even microprocessor, these are called a microprocessor, DAC and amplifier. These are my control elements. So control elements, and this is the actuator, that is the system element or the process element. These are in the feed forward path of this speed control system. So this path that you can see is called as the forward path, and this path, as the direction you can see, this is called as a feedback path, okay, of a control system. So this microprocessor acts as my comparator. Even if you remember, we had studied operational amplifiers and we had studied some aspects of comparison. So microprocessor will do the work of comparison also. Comparison of what? Comparison of desired output with the actual output. How the actual output I am going to measure? Motor, I'll be having some sensor connected to the output shaft of the motor. That can be a tacho generator, that can be an encoder, or that can be any speed sensing device, so to say. So tacho generator converts the speed signal. It is a sensor transducer. It converts the speed signal into equivalent analog voltage. Now this equivalent analog voltage is converted into digital signal by using A to D converter. I repeat, this is my system or the motor which is running at certain RPM or with some angular velocity. So that signal will be picked up by the sensor. In this case, it is a tacho generator. Tacho corresponds to speed and generator is the generator principle. The speed is converted into equivalent analog voltage. So this is the analog signal tacho generator is generating, and this analog signal is appropriately converted into digital signal. Now this digital signal is sent to my microprocessor. What microprocessor does here? It receives this feedback signal. It already has a set input or the desired output. So desired RPM, let us say, is 700 RPM. And right now, as the signal picked up by the sensor, it is about 650 RPM. So it will, of course, this signal will always be in a digital form. It will not be in the form of speed. It will be in the form of some If it is analog signal, it will be in the form of some electrical signal, maybe voltage, maybe current, or in the form of the binary digits corresponding to that speed. Now, here the comparison takes place. How much is the deficit between the desired output and the actual output? As we have seen the case, 700 RPM is my requirement. Corresponding to that, I'll be having some digital signal, and actual speed is maybe 650 RPM. Corresponding to 650 RPM, I'll be having a representative digital signal. These will be compared. So digital comparator will compare the signal, and error signal will be generated. Now this error signal, in this case, 700 is my desired output, and right now the speed is less than 700. So desired minus actual is the positive error signal. So I want increase in the speed. So this microprocessor carries out the comparison, and that error signal will be in the digital form. That digital signal will be converted into analog signal. Now this D2A converter will convert that error signal, digital error signal, into analog signal. Now that analog signal will be amplified, and this amplified analog signal will be given to motor. Now in motor also, I can either have a field control DC motor, I can have armature control DC motor. Appropriately, that error voltage will be given to this motor, and till what time this error signal will be given? Till my RPM becomes equal to 700, because 700 RPM is my desired RPM, and right now the RPM is 650 RPM. So that deficit is to be covered. Now how that is going to be assessed? As the speed of 650, as I provide additional voltage, the motor will start running at higher speed. So the speed, at the increased speed, will be sensed by my tacho generator once again. 650, 660, 670, and accordingly the error signal or the feedback signal will go on increasing, 650, 660, 670, and the error signal will go on decreasing. Accordingly, the voltage to the motor will be reduced. Till what time? Till 700. Desired RPM becomes equal to actual RPM. So once the error signal becomes 0, this microprocessor will not generate any error signal. So to the motor, there will not be any further input that is provided. Okay, only the output required to maintain 700 RPM only will be provided to the motor. Okay, so this is how this is called as a feedback control system, because the desired output signal is fed back, is sensed and fed back, and the corrective action is taken up. There is another method called as open loop control system also, wherein there will not be any feedback. That we'll see in the 5th unit where we'll study control systems in details. Okay, here I have feedback control system, speed control system of DC motor by using a tacho generator. Okay, so I repeat, if I start from left hand side, desired input, this will be my feedback signal. Here microprocessor will do the work of comparator. So I have a comparator. So desired input, comparator or error detector. Then I have, what are these two elements we call? These two elements we call as control elements. So comparator, control elements, then system or process, and then I have these two as my feedback signal. So this is how I can have a block diagram representation. Quickly we'll see the other two methods, wherein what is the difference? See, the desired input signal and the feedback signal are same. Microprocessor is same. Digital signal is generated by the microprocessor. What is this digital signal generated by the microprocessor? It is an error signal. D2A converter, analog, this part is same. What is the difference then? Instead of a tacho generator which was generating analog signal, I am using some optical encoder. If you remember, in the initial chapters we studied, in sensor transducer chapter we studied encoder, optical encoder. So it is a graded plate which is connected to the output shaft, and I have the optical sensors. So that speed signal will be converted into encoded digital signal. So instead of analog signal as it is generated by tacho generator, here the encoder will be generating a digital signal, equivalent digital signal corresponding to the speed. So instead of analog signal, I'll be having a digital signal. Now with this digital signal can be a simple binary digit. It can be a 4-bit word, it can be 8-bit word. It depends on the type of encoder I have used. Now I can use one more unit called as the code converter. Now code converter can convert 4-bit code into maybe 8-bit code, or it can convert the binary digit into hexadecimal unit or hexadecimal code. What is hexadecimal? So 16, hexa corresponds to 16. So to the base of 16, all the numbers would be converted. Like in binary, all the numbers are based on to the base of 2. So hexadecimal. So that binary digit can be converted into hexadecimal code. Why I am converting into hexadecimal code? Maybe my microprocessor here is receiving only hexadecimal numbers. So it all depends on my requirement. Like if the microprocessor can read the bit or the binary digit directly, it can. I no need to use the code converter, right? So what is the difference? Instead of analog signal, I have digital feedback signal, and that will be processed, and the corrective action will be taken. Okay, so this is the second type of speed control of DC motor, and the third type that you can see here is what are the similarities? Okay, desired input, desired output, comparison is done by microprocessor, digital signal is generated. Now the controller elements are different now. Earlier they were D2A converter and amplifier. Here pulse width modulation circuit, PWM circuit, and I have a drive circuit which will drive the motor. Okay, see, this is the only difference. My control elements have changed now. My control elements here are PWM, that is pulse width modulation circuit, and drive circuit. If you remember, what was this pulse width modulation circuit? PWM, the width of the pulses was changed. What will be the effect? The average voltage that is given by the circuit will be varying. Okay, so in effect, it will be changing the voltage only, either by amplitude modulation, by changing the amplitude of the pulse, or by changing the width of the pulse. This is what we studied earlier. So here it is changing the width of the pulse and it is varying the voltage. Accordingly, the speed of the motor will be altered. Till what point? Till the actual speed becomes equal to my desired speed. So this is how the speed control. Here also I have, what are the changes? Other things are same. Only thing is that the control elements have changed. So this is how the speed control of DC motor system works. I think next lecture is there. So we'll stop for today.